Okay, so today I work on the sixth exercise from I am Tom's uh, repository of exercises. Last one was a bit tricky. It was about was it data kinds or rank-n types? I don't remember. Yeah, rank-n types. And this one is about type families. So as usual, I'll go through the explanation file and now try doing the exercises. Today's module will be a very brief introduction to type families and their uses. We're not going to go where Song or Stalk went. Okay, no idea what Talk is talking about. Though there is plenty of further reading to be done if you're interested. Okay, so we have our usual familiar data net, which is either a zero or a successor of a net. Yeah, we're hopefully all aware of value level functions. So we have an add function which takes a natural, another natural, returns a natural. So if you're adding 0 to y, we get back a y, of course. And if you're getting two naturals, yeah, gets pattern matches on the x to get the successor, and returns the successor of adding x to y. So this recurses until it's the 0 here. Makes sense. Returns our new natural. Type families, by their simplest definition, are functions at the type level. Yeah, and I wonder why they didn't choose a name that reflects this a little more. Probably because there's more behind type families than just this. But in case you're wondering, the type families extension implies the kind signatures extension. Makes sense. So we have a type family add. Okay. So it looks, yeah, a little bit the mixer between JDT and a normal family for the syntax they're using. So a type family add, which takes an x which is of kind natural, a y which is of kind natural, and returns a natural. Where add 0y, well, this is the same as this one, except we're using types and we're not using values. The syntax is a bit funny, but hopefully the symmetry is obvious. We specify the parameters in the first line, as well as the return type, and then we write equations on the subsequent lines. Technically, this is a closed type family. We specify all equations up front, like a value level function. Okay. There are also open type families, which behave more like type classes, but we don't pay them too much attention. Okay. So there's a type family open, which takes a type, x and returns a type, and then you can write the type instance. Interesting. Okay. Okay, cool. So why will this be useful? Well, we'll say the fun examples for the exercises, as most of these are pretty intuitive. But let's pick a nice easy one. A while ago we talked about the singleton boolean type. Yeah, it was in one of the exercises. So we have an sbool, which takes a value of kind bool. Then we can have strue, which is an sbool type true, and sfalse, which is sbool which wraps a type false. What if we wanted to flip the boolean value? What would be the type signature be, as well as the value level not? We need a type level equivalent to match. We can define this quite neatly as a type family. Type family not, which takes an input of kind boolean and returns a boolean, where not true is false and not false is true. Yeah. Now you can write the function and its signature. So not takes an sbool input, returns an sbool of not input. Yeah, Okay, so this that works at type level, and this that works at value levels. Okay. I can already see that I'll be pretty confused by stuff in exercises. But the input type determines what the output type will be. Yeah. And a type family will be evaluated for each pattern match in our function. That's all there is to it. One last thing that might be of interest. Type families don't necessarily have to be total. So we have a type family subtract, takes two naturals and a natural, returns a natural, where subtract x0 is x, and subtract sx, sy, subtract of x and y. Okay, so subtracts the second value from the first. However, it doesn't deal with the possibility that the second value is bigger than the first, because we don't have any way of representing negative numbers. So what happens when we get it wrong? Let's load up GHCI with cable REPL. Okay, let's try. Haskell exercises. This is 06. Cabal REPL. So we can set data kind. Kind subtract the successor of 0. We have to add type families. Oh, my bad. Okay, so this is the first time we've played with GHCI, so notice a couple of things. Yeah, this set is our return language extensions. The kind count will tell us the kind of an extension. Yeah, that's not extension. While the kind with the bang will tell us normalized form of the type. In our case, that means evaluating type families as far as we can. So what happened? Well, if we can't find an equation that matches our call to a type family, we can reduce the expression and it stays how it is. This is part due to things like open type families. We might work out how to reduce the type family later on, so we can definitely say it's an error. Okay, so I guess if we try kind subtract s0 0. Oh, come on. Return s0, and then we can try something more fun. So it's 2 minus 1, returns 1. It's pretty neat. Okay. In this particular case, we see our expression is stuck. We're not going to go into any further detail about what this means, but talk to Xongod if you're interested in the ways you can misuse this. Yeah, okay, we're not gonna bother him. Now let's check the exercises. Okay, before we get started, let's talk about the type operators extension. All this does is allow us to write types whose names are operators, and write regular names as infix names with the backticks. Okay. As we would at the value level. Okay, makes sense. Again, our natural. Use the type operators extensions to rewrite the add family with the name plus. Okay. So let's write again our type family add first. Takes a nat, takes another nat, returns a nat, where add x z. Was this how it worked? Equals x. No, I think it's. I'm not sure. No, it was correct. Okay. No, but the recurses on the first value. Okay. Sorry. Y equals y. Oh, come on. Why is it? Emacs is struggling a bit for some reason. Now we have a successor of x and a y, and then it's just the successor of add xy. Okay, these are type family add. Use the type operators extensions to rewrite the add family with the name plus. Can I just do this? Do I need backticks? Not bad. I wonder, maybe I just need to do this. Sorry, it's z plus y and plus y. Operator applied to too few. Okay, this is how it works. Obviously, yeah, it's an infix operator, so we have to put it between arguments. Write the type family that multiplies two naturals using plus. Which extension are you being told to enable? Why? Let's see. Type family. I'm gonna embarrass myself by not being able to do primary level school operations. Times. Why is it using two stars instead of one? So if we have okay, so if you have 0 times y, return 0. If you have x times 0, return 0. I guess we have to cover these cases, right? What else? If we have successor of 0 times y, return y. Our y's. I guess he's gonna be an x times where is it? Y plus y. So we don't really need this case because we can handle 0 plus 0 fine. Do we need this one? I guess so. Do we need this one? Yes. Legal nested type family application. Use undecidable instances. I don't know why we're asked to use this extension. So looks like this works. Let's try exercises. Let's try doing something. So let's try 0 times 0. Yeah, we need to why was it complaining? Does this work? Type operator also. Do we need type families too? Oh, we need to do this, I guess. Okay, so 0 plus 0, 0 plus 1. Okay, looks like it works. Let's try 1 plus 1, just to be sure. And we got 2, so this works. Let's try multiplications. So we have 0 times 1. We need the kind of this stuff. Come on. Kind. We got 0. Okay, it looks correct. Kind of 1 times 2. It's 2. Let's try 2 times 2. And it's 4, so it works. Nice, 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 nice. I'm still unsure if we actually need this stuff. We need this one for sure. So if we are the successor of 0, can we write it? So y plus x times y. Yeah, then we don't need this. Yeah, okay. Data as nat. Takes a value of kind natural. You have SZ, which is kind type as natural of 0, and success. Okay, write a function to add two SNAT values. Okay, we did something similar here, right? Okay. Okay. So we have add, which take an s nat x, an s nat y, returns an s nat of x plus y. Yeah. So I just need to check the work Slack. Yeah, no one is looking for me. Sound good. Okay. So we can add two as nats. I guess we can do as we did before. So if you have SZ and a Y, we return a Y. And if we're adding an SSX and a Y, we can return the SS of add XY. Okay, looks like it's working. Let's try again. So we can add SS, SZ, SS, SS, SZ. There's no show. Where is it? I don't think we can derive show for GDT, right? Yeah. We need some parentheses here. And we should be good. Okay, so let's reload. Let's add the stuff, and we get 3 because we're adding 1 plus 2. Works. Cool. Okay, now our friend Vector. How many of these are here? 9. Oh my god, it's gonna be hard. Vector, which encodes its length as a count, and return type. So we have venial, which is a vector which has length 0. And becounts with a vector takes an a, another vector length 10, and returns a vector which is length n plus 1. Write a function that appends two vectors together. What would the sides of the result be? We can use our add. Right? So the result length is m plus n. So we can append venial y, and we return just y. So far so good. And then we can append we don't want to flip this vector, right? So we can have a v counts x and rest, and we have a vector v, and then this can be just a v counts of x append xs y. Yes, this one looks good. Looks good. Should we try it? We need to write an instance for this. Show vector and y where oh no, I don't remember anymore if this is how you write these things. Show v nil. We can just return this. We can do a show x. Show access. Okay, and then we can try appending vcounts 1, vcounts 2, v nil to vcounts 3, v nil. Well, let's 4, v nil. Yes. Nice. We get 1, 2, 3, 4, and then the vector ends. Okay, write a flat map function that takes a vector and a function that goes from a to vector mb and produces a list that is the concatenation of these results. This could end up being a deceptively big job. What does flat map do? I don't remember. Oh, because it's loaded this one. Okay. Let's call it this. Okay. Stack age, help us. Full map. Okay, map each element of the structure to a monoid and combine the results. Okay, so I guess we have to use our multiplying thing. So the new length is going to be n times m. So if we have an empty vector, we're just going to return the empty vector, of course. If we have a vector which is not empty, so we need these append functions for sure. So what we know is that fx is a vector mb. So we can just append f of x to flat map x f, I guess. Get an error. Sorry, excess. Looks good. We should try if this works though. Sorry, oh come on. Okay. So let's try flat map. We have v counts 1, v v const 2, v nil, and we can use a function that takes an int, and is there like a repeat function? Can you like take a of repeat x? Will this work? I'm getting a lot of errors. Well, let's try it. Take 3. Okay, this works for sure. Oh, I have to return a vector. Right. My bad. Okay, let's... Let's create this. So this one takes an integer. Does it? Yeah, takes an integer. I can encode these at type levels, right? Yeah, I can do this. It has to be a fixed length. Okay, I guess we can add the value to itself. So let's see, let's create a vector. Which has length 2. What I can do is do a v count first element squared, then times 3. Okay, so let's try flat map. So we can use 3 and 4. Possible build vec function. I get 9, 27, 16, 64. So this works. Okay, we're good. Number 3. More Boolean fun. Write the type level and the function for Booleans. I'm gonna open this one though. So yeah, it's a type family. And sorry, x bool and y bool, which returns bool. So if we have false, can we do this with type families? I get I get no error. Let's see, I'm gonna try them. And then we have a type family x bool or y bool bool true. Actually, looking this at the wrong side. We can do it if it's true and true, much better. It's true. Otherwise, it's false. And if we have false or false, I'm very annoyed that Emacs is adding the double ticks. We have false, otherwise we get true. Okay, let's try it. Let's check the kind of true and false. It works. Cool, works. Nice. Write an all function that returns true if all the values in a type level list of booleans are true. So is this still a type family or a regular function? I'm not sure. Guess makes sense for it to be type family. Then after we have the type family, we can write the value level function. So type family all, which takes this, returns this. I don't know what I'm doing. How do we do this? Oh, we need the tick, maybe. Yeah, because here in the signature we don't need the ticks because it knows that we're talking about kinds. And here it needs to know that we're talking about a type and not a value, I guess. Which I don't know why. I mean, it should be enough. In my head, I don't know. So this works. try the kind of all. True. What am I doing wrong? Parser on input. I don't know why only the external one is needed, not the internal one, honestly. True, true. True, true, false. It's false. Okay. 4. Not fun. I have to remember that I have to check this one. Why we need undecidable instances for this. I guess because I'm using another type family here. I'm not sure. Not fun. Write a type level compare function using the promoted ordering type. Okay. What's ordering? Not sure. Should be the prelude, which maybe it's not loaded. Okay, that's LT, EQ, GT. Okay, so we have a type family compare. I'm gonna have a nat, another nat, and we're gonna return an ordering. Format. Scope ordering. Okay. So let's see. If we have 2 zeros, we can return a Q. If we have a compare of something, which is not at 0, of course, because I already matched on at 0 here and 0. We have GT. It's probably a better way with less things to write this. So what if then if we're comparing the successor of an X and a Y? Oh, how's this gonna work? Oh, we're just subtract 1 from each and compare them again, right? Looks like it's working. Not in scope show. Oh, so ordering is not in the prelude anymore. So it's here. It should also be in the prelude. Why is it not? not in scope, data constructor ordering. Oh, is it because of the tick? Okay. Okay, so we can compare 2 and 1. We need kind, and it's greater 2 and 2, and it's equal. And then I guess we can try 2 and 1, and it's lesser. Nice. Nice. Write a max family to get the maximum of 2 natural numbers. Okay. So a type family which takes a natural, takes another natural, and returns a natural. Yeah, and this is the easy part, I guess. Oh, I need a name, max. So I messed up the easy part. Okay. Can we do something like this? Swy case compare. I'm not sure if this is allowed at all. If it's EQ, return X, greater, return X, or even better, if it's LT, return Y, otherwise return X. I think we can't do this. Too bad. So if it's max 0 and Y, we can return Y. Or we can do this maybe, max X, Y. Can I do this stuff? I'm confused. Probably not. Y, else, X. No, this sucks. Just checking my work messages very quickly. Looks good. Okay, so this doesn't work. This doesn't work. So let's try writing each cases and then we can see if we can reduce this to something nicer. So if we have the max between 0 and y, it's y. If you have the max between x and 0, it's x. If you have the max of the successor of x, no, we can't do this because this way we won't have the actual max value. You just know we just return 1 every time. How do we do this? How do we do this? Oh, this is very interesting. So I can use compare if, like if it were a normal function. I wonder what I'm allowed to do. I can call other type families for sure. Oh, maybe I have to use the tick. Max xy. Oh no, it's the if the problem. I guess there's no type level if. Yeah. Right. Type level if. I don't know. Maybe. Or maybe I can use an helper function. Can I? Can I write like a type family max, which takes takes a compare. Yes. Nat. Nat. Where max less than turns y turns x. It's just gonna be max compare xy. No, this one is an ordering, and should return nat. Looks like it's working. So I can find the max of 1 and 2. And it's 2. Cool. Can we try writing the if type family? Let's try. I'm curious to know if it's possible to write it. So let's see. So we have a type family if. Oh yeah, no, I don't think it's possible. It needs a bool. And that takes yeah, no, actually we're writing max this way. Expression type A returns an A if true, if polykines. Okay. And then we need a type family is greater. Takes an at. Takes another nat. Returns a boolean. Is greater. Sorry, so y. XY. So annoying. Looks like I'm going in circles. Is greater 0 0. This can say it's true. Is greater 0 is false. Greater x 0 true. So yeah, I guess we can write it like this. No, we can't. We need to do this. And then is greater successor of x, successor of y is greater xy. And now we can write our type. We can try writing the type family max2, which takes an at, returns an at, max2 xy is if is greater xy x y.
I'll get straight to the point. I found marijuana in the house. And while I never thought of myself as the type of father,
Can't believe it. Looks like it's working.
Just that, if that's what it takes to find out who brought a joint into this house.
Dad, Lucy found.
We're not actually using compare though.
Found the joint in Mom's dresser drawer.
Right. So this one works, but actually I should be using compare here. Right. So I need a type family. This is confusing. I don't know. I don't think I can do it. I mean, it's probably possible I have to write like a couple of more type families and then fix them to natural typing. I don't know. And this, I feel like this is already interesting enough. I mean, of course, I can write this using compare and helper function. Well, it doesn't make much sense. Write a family to get the maximum natural in a list. Type family max list. This one takes list of naturals, returns a natural. Max list. Probably have to use no, I can't really do this. So no, yeah, we need an accumulator for sure. So it's gonna be max list 0 access. Max list takes, yeah, accumulator. Maybe it's not the wrong name, but that max list. So if we're done, return A. Then return max list max AX access. Looks like it's working. Let's try it. It's gonna be very annoying to write this. Max list. Can I avoid ticks here? It works. Let's add successor of 0. 1, 2, 3, 4. Nice, it works. Okay, let's move on to the next exercise. 5. Oh, we are a nice tree. So we have a tree which is empty. Where is a node? Tree, not tree. Okay. Write a type family to insert a promoted nat into a promoted tree. which takes a nat, takes a tree, and I guess returns a tree. Right? So I never studied algorithms or anything, so I'm not sure what this is supposed to do. Where is it inserting the natural? On the left, on the right, the top? Well, something I can check do for sure is that if inserting something to an empty tree, we can just return a node of empty x empty. And this one looks like it's working. Then if you're inserting inside of a node, just left, sorry. I guess we're just gonna add it to the left branch. I don't know. I guess it doesn't make that much of a difference. There are probably different names for different criteria how to do this. I'm gonna check solutions because I'm not sure about this one. I wanted to check the solutions for this one too. And there was another one. There was another one, right? Maybe this one. Looks like it's working. Let's try kind of insert. Let's insert one into an empty tree. Wait, it's not being evaluated, right? So it means that this is not working. Why? I'm calling insert of a natural and an empty tree. I should return this one. Why is it not returning this one? Oh, because I didn't use the bank. Okay, node empty, one empty. Okay, cool, this one works. Now we want to add this to a node. Let's say there's an empty branch, 0, empty branch. So we have a node that has 1 on the left, and yeah, works. It added 1 to the left node. Probably this is what is called left balance tree. I don't know. 6. Write a type family to delete a promoted nat from a promoted tree. What? I'm gonna have to check solutions for this one for sure afterwards. Type family delete xnat t, it's a tree, and return another tree. So if you're deleting something from the empty tree, guess we just return the empty tree. Then we want to delete something. From a node. Well, our So what happens if I delete a node? Do I delete everything that's below it? This is tricky. So there's something wrong here, I guess. I don't think trees work like this, right? I have no idea how trees work. Am I supposed to always add it on the left, or does it depend on the values? Let's try. Let's learn from pictures. Yeah, I think it's supposed to work like this. So a starting node, and if it's lesser, we go left. If it's higher, we go right. So now we're adding 4, we go left. At 12, we go right. We add 10, go right, then we go left. Makes sense. So this one is wrong. Base case is correct. Base case looks good. This one is wrong. We need to compare these two values and then do something. So I guess we can try this. Compare xn x. Can I do this with TypeFamilies? Oh, let's comment this one. So now we have an ordering, our nat, our tree. We're returning a tree. So if we have a less than, so it means that the thing we are adding is smaller. Then I guess returning a node where we insert x on the left. If it's greater, we return a node where we insert, insert on the right. And if they're equal, we just return a tree. I suppose we don't do anything if they're equal. Okay, this compiles. I can do this. Okay. So, wait a second. Need to check again. Okay, this compiles. This is probably gonna be very annoying to write though. Type. Let's write a few numbers. 2. Successor of 0. Tree, which is the success. Can I do this? after we inserted 5, after we inserted 3 in a node empty 2 empty. Okay, looks much better. Where is it? So we have a node which is 1, which is on the left of 2, which is our central node. Then on the right we have 3 and we have 5 on its right. Good, okay. Okay, this one works fine. Now we need to delete. So what happens when we delete something from a tree? Do we need to rebalance the whole tree? I don't know. So let's say that we have let's say we have a tree, 2 here, 5 here, empty, empty, or maybe there's a 1 here. There's 4 here. There are 6 here. And then these are empty. So when I delete the node, I guess it needs to find the smallest of these two. This is tricky. So the 2 goes up here. Let's change the numbers. I need bigger numbers. 8, 6, 7. We can have this 0. We can omit the empty. So everything below here is empty. So let's say that I delete the 5. So the new top node becomes the 2, because it's the smallest of this. I'm assuming. Then what happens here? Oh wait, this is wrong. This can't happen. So this becomes the 0. I'm guaranteed that all the numbers that are on the left are smaller than the numbers on the right. So I can put as the node here, the left node. If it's not empty, otherwise the right node. I need bigger numbers to visualize this. Let's do it times 10. Oops. I'm sorry. really don't know how to work with trees, so I'm reinventing the wheel. Okay, then here we have a 2, 3. No, this is wrong. This is not how it works. This is wrong. Let's write it from scratch. So I have a 50. I'm adding a 0, it goes left. Then I'm adding an 80 and it goes right. Then I'm adding a 10, it goes left, then it goes right. Then I'm adding a 20, it goes left, it goes right, and then it goes right. Then I'm adding a 2, it goes left, it goes right. Oh, I have no idea how this works. So 2 is smaller than 50, yes. 2 is bigger than 0. Yes. 2 is smaller than 10. So it goes here. Then I'm adding 3. And 3 goes here. Right? Let's check her back here. Yes. Then we add 60. I think it's gonna be very complicated. And 60 goes here. Then we add a 70. 70 goes here. Then we add a 55. And 55 goes here. And then we add 62. 62 goes here. Then we add the 90. And 90 goes here. And then we add an 85 greater, greater. And it goes here. I guess. Okay, so we have our tree. Let's think of an algorithm. So let's say we to delete node n. If n is not equal to our node, we keep on searching. If n equals our node, then we can delete it. What does it mean deleting a node? What does it mean? So let's try here. Let's say that we want to delete the 50. So I'm assuming we're gonna replace it with the left node. So we're gonna have it 0 here. And I'm gonna assume we keep the right side as it is. So we're not gonna touch the 80 and everything that's below. What happens here? Let's say that we have, let's make this an 8, sorry. Let's make this an 11. Let's make this 4. And add 3 here. Okay, so here we have an 8. And we can keep the right as it is. But I guess we have to do something with the left side. Can we promote? So put 4 here. Yes, we can count it as we are deleting the next node. So the 4 goes here. We keep the right side as it is. We promote the left side. And then we're done because everything is empty. So we keep the right as it is. We replace the top, the deleted node with head left and recursively go down. Okay, well, makes more or less sense. Let's try something. So if you're deleting something from an empty tree, we can return the empty tree. And I guess this is gonna be our end stop here. Now we want to delete something from a tree which is not empty. So we're gonna have to compare the natural we are using. We are gonna have to compare the natural we're using with the node. So I don't know how I'm gonna call this. So we are in a new type family. Let's call it foo. Just gonna have an ordering, nat, and tree. Let's call it delete. It makes sense. It's the same name we used before. So we can do a delete, compare x and x, node L and R. So if you're deleting and it's less, I don't think this is going to work. And we have an X and a 3. Then we are gonna return a 3, which calls delete on the left side. Oh no, maybe it works this way. Okay. I'm gonna return. I'm gonna return a 3, just the left, and delete XR. Now it's the tricky part, because when we get to the equal case, so we're returning a node, just something on the left. We don't know nothing about this, but we know that we're keeping the right. Let's see, if we have a get node, it gets a 3, returns a natural. This can return always a natural. Now maybe we can be sure that we never hit the empty 3 case by carefully matching here. Let's see. So this one returns n. So we can call get node L. Here we can delete get node L. Expecting one more argument. Oh, it's delete. I have no errors, but I'm not sure this works. And I'm even sure how to represent this, honestly. Let's try writing a very simple tree that it's easy to visualize. Let's say I have a 2. I can have a 19 here. So let's put a 5 here. Let's have a so a 3. Let's have a 2. And let's have 4. So after deleting 5, This one should become 3, 2, 19, 4 ideally. This is never gonna work. I'm 100% sure. So type 3.1 is gonna be so we have a node empty 5 empty. We insert 3. Let's close the parentheses afterwards. Then we insert 2. Then we insert 4. And then we insert 19. Okay. There's no 4. Type 4, 2 plus 2. Okay, let's kind 3.1. So there's a 1, 2, 3, 4, 5. There's 19 on the left. There's a 3 and 2, 4. Okay, the 3 is correct. Now let's try kind. Delete 5, 3, 1. There's 3 with 19 on the left, which is correct. There's 2. Oh, yeah. Yeah. It's almost working. The problem is that we hit the empty case here, and get node is not able to return. I guess we can do this. Wait. Yeah, we don't need this. We can do this. So if we are if the left is empty, you just return the right. So if both are empty, and if it's an empty tree, we can return the empty tree. Alright. Otherwise, here, this is tricky. I don't know. Let's return the tree, which is empty here. Should get node R here. So again, we have our tree, 19 on the right, 2 on the left, and it doesn't work. Why not? So we're calling delete. 5 on this tree. So it calls delete, compare, okay, and it's equal. Let's say is left, we're here. Is left empty? Is it... Oh, this is wrong. So we're here. It's not empty, so it doesn't matter much on this one. So it goes here. So we have left and right. So it creates a new node, which has tree as the top, and has delete tree from this tree here. And it goes right. Okay, so delete tree from this tree. These are not empty. So it goes 2, 4, and then it goes delete 2 from 2. Okay, so instead of this one, I think we need delete node.
What this is saying then is that just as you don't know how you manage to be conscious, how you manage to grow and shape this body of yours, that doesn't mean to say that you're not doing it.
There are no get nodes now, so it looks better. So we have
How the universe
our
shines
node
the
3
stars,
with 19 on the
constellates
right,
the constellation, and galactifies
and
the
there is a
galaxies.
node
You
with
don't know. But that doesn't mean to say
2 and 4 on the right. Looks good.
that you
It actually looks
aren't
correct.
doing it in just the same
So
way
I'm not
as you're
sure if
doing
this is
it
going
without
to
knowing
work
how you
for
breathe.
more complex cases, because this is a nightmare to visualize. So let's try node empty 0 empty. Let's call this zeta tree. Okay, let's create a tree too, so we can let's try using our numbers. Let's try inserting 11. Insert insert 1. Insert 2. Insert 8. Insert 5. Insert 3. Insert 4. Insert 19. 0 zeta 3. Yeah. I'm not going to do this. It's too complex. Too complex. I'm getting a get node, so I already know that this is wrong. Well, this is broken. It's too hard to visualize, so I'm going to give up. I mean, I guess the idea is pretty much this one. We're gonna change some stuff here and there. So with type operators, we can use regular Haskell list syntax on the type level, which I think is much tighter than anything we could define. HList. Okay, write a function that appends to HList. H append, because I think we're ready. Oh, sorry. Type family H append, which takes a list, takes another list, we define an append, right? And those for vectors. So we're able to do this with vectors because vectors are the length encoded. Oh wait, yeah, we can do this because we don't know the length. So we have another return at ZAS. Do we need type families for this? So we're appending hnail to something else, return something else. If we are appending, there's something in that previous exercise consumed all my brain energy. with x, y, ys. Okay, and this return an h list. What kind of h list does it return? Let's try this first. Yeah, sometimes it understands that it's a promoted constructor, sometimes it doesn't. Does this work? Looks way too easy compared to the previous exercise. I'm gonna guess this is wrong. Let's try yeah, it's not working. It's not evaluating the expression. So yeah. But the compiler doesn't give us a lot of help, right? Okay, I'm gonna have a 30-second break and I'll be back.
Mic off. Mic on.
Okay, I'm back, sorry. So we're trying to do this exercise. So what does it mean appending to each list? So an each list could be like and another each list could be b h comes true and so the final type of each list 1 each list 2 would be each counts 1 each counts low h counts b h counts true h nil. So obviously we need to be able to encode this at the type level. Sorry, just a second.
Mic off. Mic on.
Okay, sorry, I'm back. Okay, so we need to encode this stuff at the type level somehow. Right? So this one is a list. This one is a list. Ideally, you would be able to do something like this. It's not true we can use regular syntax. No, we're not allowed. No, maybe this is what we have to do. So we have an append, which take an h list of xs, an h list of ys, and an h list of xs plus ys. Okay. So we have create type family. which returns so if we append the empty list to something, return that something. And if we have access plus yes, return x. Type family append. Do I need parentheses? Oh wait, I don't need the name. I already have the plus plus. So tired, getting so hard. Oh yeah, I need the name. Access. YS. Append. So we can replicate what we wrote above. So if chnil ys was ys, h counts x success ys, it's h counts of x, append access ys. Cool, it works. And I'm pretty sure this is correct. So we can go to 8 and 9. Right. I think I'm gonna stop here. And gonna check the few things that I wasn't sure about. So GitHub, Tom, Haskell exercises, TypeFamilies, answers, exercises. Okay, so 1.b. Why? Okay. We don't know why. We're not allowed to know. 4.b. Max. Yeah, it's the same. 5. Insert node T. Yeah, this one looks good. Good job, Dario. 6. Super ugly. All okay. This first line is the same. The second line is the same. Cool. We can't let bind the result of a function like compare, so we have to have a helper family to compute the above. Okay, well, yeah. So we have delete lt, node. It looks the same so far. Looks the same so far. Yeah, these were what's. Yeah, so when left is empty. And R, it just returns R. Okay, then this stuff here is completely wrong. So what it does is delete node al R, does a repair, biggest all R. You also can have an helper family for the last case above, so we need 2 more helper families. So there's a repair. Which puts then this left node as the center. Okay, makes sense. And the biggest. Okay, so let's try going through this. Is a repair and a biggest. So let's write biggest first. So it takes a tree and it turns a tuple of a natural and a tree. So if I have a tree where the right is empty, it just returns the node as the number and the left tree. Okay, makes sense. What happens in this case? So I'm not entirely sure what it's supposed to do. So if I have a tree which is not empty in any branch, or at least it's empty on both, use this helper function, biggest. What? This biggest quote takes a tree. A nut. And the result of biggest on the right side. I don't know. I'll never be able to write this function, honestly. Returns again tuple, not tree. Where biggest of the left, which is a tree, center, which is a tree, and this thing here is x, because of course x is going to be the biggest number here, with node LCR. Okay, and then we have a type family. These are type families, not types. Which takes parts, which is a nut tree. Takes a tree, returns a tree. Oh, nice. And then it writes stuff to write tests, which makes sense. Let's try going through this and see if I can understand what's going on. So this part is the same. So if left is empty, and I have right, I just put the right there in place of. I wonder what's not doing the same thing if right is empty. It's probably covered by this, but so if right is not empty, it calls repair on the biggest L and then R. So let's say that right is empty. Right is put back here, so it doesn't care. If it's empty, it stays empty. correct. Okay, so there's no need to pattern match on the empty right case here. Sorry, I'm a little lost. Okay, repair. And then it does this biggest stuff on the left node, and with the result, it rebuilds this node. So I guess this repair is a little what I was thinking about, but it wasn't working. So what happens with repair? Sorry, with biggest. So biggest of a tree. Oh, so it rebuilds everything. So if the right side is empty, our center is the biggest, because everything that's on the left is gonna be smaller. And so we turn the center and the left tree. If the right is not empty, then the biggest is gonna be on the right side. So it's rebuilding the tree. I don't know why it's doing that though. Oh, let's maybe I want to check if this one is correct. Sorry, just a second. Node empty x empty, insert compare x. Yeah, no, this one is correct. Okay. So it calls biggest quote, so it finds the biggest on the right side. That calls this biggest L left center. So the left center. So it threads the biggest number up and it rebuilds all the tree. Okay, well, I mean, it makes sense, but I will need to be able to visualize this stuff somehow to be able to write these functions. It looks very complex. So let's check solutions for 7. Type family, yeah. Okay, this is correct. Okay. Now I'll leave 8 and 9 for next time because I'm super tired.